Hey guys, we were receiving multiple grievances about the sound quality of the STA series from multiple viewers over a long period of time. It took our serious attention. As a solution, we are republishing STA episodes by digitally remastering the audio. In this video, we will install the Opentimer STA tool in Ubuntu Linux with vivid detailed steps. In the next sections, you will be ramped up in Opentimer STA to validate, set up or hold concepts in real test cases. You will learn how to do various analysis such as slew, slack, arrival time, required arrival time, leakage power, consolidated reporting and pin-wise reporting using Opentimer command prompt. Next, we will do path tracing for setup or hold with AT versus RAT comparison. Next, we will cure STA violations using gate sizing method for both setup or hold violations. Finally, we will apply what if then analysis combined with gate sizing. So stay tuned, stay focused. Hey guys, in today's episode, we are installing one particular free and open source static timing analysis engine. Its name is Opentimer. You can see in the screen, here is the URL github.com opentimer/Opentimer. So all these links will be provided in the description of this video. And at present, this particular software is available in Linux platform only. So we will install this. I have a Ubuntu system with me and I will install it. So here, before going to give me a short introduction, what is Opentimer? Opentimer is a static timing analysis tool and it's an open source tool. So if you are a software developer, you can contribute, or in case you are a VLSI engineer, you can use it after you install in your Linux system. This Opentimer is a kind of tool which is very much look-alike in operation. It's also very much look-alike with the industry standard static timing analysis tools. Here the shell looks like this. Once we install, we can see that how this will come up. Here is the system requirements and the build instructions. Dependency is that you must have TCL/SH. Let me install it for you, and without further delay, let's begin. This is the instruction here, how to install it. This is the URL. So this URL, if you go and visit, you will get all these system requirements and how we can install it to our command line interface. So let's start. I am at my home directory. Let me make one directory here. So I am making a hidden directory .opentimer so that there is no visibility of this directory to side by side of the visible directories. Okay, so let me change my directory. Now let me execute the first command here. And by the way, I am online now, so it will be done through so we cannot find GIT. Install GIT. So what happened that the first command we had the command GIT and we cannot find it. So we are installing it first. So let's see. So it is ongoing. Git is done now. So let me go back to the command. Before going that, let me check which directory we are in. So we are inside this, so we have to move to .Opentimer. Okay, so we are inside this directory, and now we'll execute the git command. So we want all the files to be cloned in our .Opentimer directory. So let me start it. It is starting. You can see that this git is cloning the entire directory here. So as you can see here, the thing is moving with a particular speed, and all the files are getting cloned. We are waiting all the files to be cloned, and then we can go to the next steps. Okay, so cloning is done. So all the files have been copied. So let me do a ls command. Okay, so it has created another directory called OpenTimer inside. So let us go inside that directory. So we are now inside the directory, and we can see here a lot of files are there. So let me go back to the instruction set again. So we have went to the OpenTimer, and here we have to execute this mkdir build. So let me write it. Let me mkdir build. Okay, so it's done. Now what is the next? Say then went to cd build. We have inside the build directory. Next is we have to make cmake dot slash cmake. Now again we face that we do not have cmake. So let me bring up the sudo command to install. Okay, and now here we install cmake. So these are real-time problems where you are installing in Ubuntu and you are trying to install something. There might be some dependencies on the go. I may have to install them. So like that, here we are facing that we do not have the cmake, and here we are installing cmake. So again, yes, okay, fine. So guys, don't get disheartened if you don't see a package, because if you are online in Ubuntu, at that time you can use the sudo apt-get install command directly to install that particular package. Okay, and these are real-time challenges. So may occur these problems where once you try to install something. Now let me see which cmake. Yeah, it's there. Now we can use the cmake command. This, okay. So now it has started compiling. So OpenTimer's request tclsh to build VLSI. So here we see another dependency is that we do not find tclsh here. Let me bring up the sudo command. Again, we have to do tclsh. This is the basic tickle interpreter. So we can see here it is asking that it will install tickle 8.6. okay, and as we execute sudo apt-get install tclsh, the repository is there already inside. If it is not there, we have to go to the particular site here as it is mentioned here, and we have to add the repository. And now I said yes, and it is going on. So let's wait. once the TCLSH start to install. Yeah, it is installing. Okay. Now it's done. Let me execute again CMake. So it is done now. It is done now. Let me check if everything is okay in the log. Okay, I think this step has executed. And then we have to use make. Okay, before executing make, let me check whether make is there. Okay, make is installed there. So I'll execute make. So the make is ongoing here right now, as you can see. So make is basically here, it is doing a local process. So online processes are done. Now in local directory, we have created a build directory. Inside that we are executing the make. So it is building that a particular software, okay, the Opentimer. Okay, so the process completed. So you can see here it has completed 100%. And now let us see what is the next. So I think this we are at the last step. So after successful build, you can find the binaries. Okay. So let me now shorten this terminal. Okay. Cleaned it. Which open. So I have made an alias here, OpenTimer as user bin OT shell. So now let me do which OT shell. Okay. So probably here we need to do a restart. Okay. Let me check. So guys, we are back after the reboot and we have entered the directory where we have done the build. So we are doing a ls here. So you can see here there is a bin directory binary. If we enter here, we can see do the ls, we can see all the binaries have been created here. Okay. So here I have set the alias to this. So let me do a ls and then to user local bin. Okay. The directory is there. We will copy all the binaries. We will use sudo as a super user. We will be copying copy tar all the binaries here into the user local bin directory. And here it is asking sudo password. And in this directory, okay, there are 4 binaries created. So we will do sudo. I have given the sudo password. So it has copied all the binaries. So let me do ls of that directory. Now all these things are there. Okay. Here what I have done, I have set a alias Opentimer, which I have done alias. Let me clean the screen and do the, okay, so I have set in my CSHRC file that I have aliased this Opentimer with user local bin OT shell. So let me start the shell. So when I execute, it opens the Opentimer shell. So guys, we have successfully installed Opentimer in our laptop or desktop, whatever PC you are having with you, local. And in this example, we have installed it in Ubuntu. For rest of any other distros, you can install as per the build command, whatever I have shown you. But I think this Opentimer is not available in Windows. Okay. So at present, you have to have a Linux system like Ubuntu or something at your end to install this. So that's all, guys. See you in the next episode. Bye. Hello and welcome to the 10th episode of Static Timing Analysis. In today's episode, you will be introduced to all Opentimer commands and report analysis. Already created a video on Opentimer installation. Link is given in the description. Here is our menu for today. First, we discuss about STA commands and flowchart with example. Second, we talk about STA report structure and analysis. Next, we talk about Opentimer license. Next, we talk about exhaustive introduction to Opentimer commands. Next, we talk about Opentimer example with commands. Then, we talk about Opentimer STA report analysis for setup violation. Then we talk about Opentimer STA report analysis for hold violation. If you want to learn STA tool, then this episode is a must for you. We are done with this particular slide, so let's move on. STA tool flow and usage. In this section, you will be introduced to all kinds of input and output files. All the input files are already covered in detail in previous episodes. You will be introduced to various kind of outputs in this episode. STA Engine input-output files at a glance. Before going further, let us have a quick glance at all input and output files of STA. So this is our STA engine. First, we have our synthesis tech library. Next, we have our gate level netlist. Next, we have SDF. We have the design constraint integral. And we have our timing library, that is timing.lib. Now, once the STA engine processes all these input files and we hit the report timing command, it generates AT or RAT report and histogram, and we can access the live design data. In case you are not familiar how to get the design data or how the engine at all accesses the design data, I have given a little episode link in the description that will clear your mind. We are done with this particular slide, so let's move on. STA commands and flow. You have just seen all the input files. Now, all of these files have to be processed in a specific manner. Here is that flowchart. We will proceed in this direction for the progress of the flow. First, we read all the input files. Next, all the constraints are activated. Then, all the inputs are validated. Next, finally, we generate all kinds of report, histogram or design data access. So, this is our short and sweet flow and we are done with this particular slide. So, let's move on. STA is command line. Now folks, this is a very important slide. For those who are experiencing the STA tool for the first time, I would like to emphasize that STA tool is a command line tool only. STA tool runs on its own shell, and the shell is always a command line. For Opentimer, the shell looks like this. So let me bring my mouse pointer. Here it is the shell started, and it gives a header printout kind of stuff. Opentimer you can read. You have probably saw this one in the thumbnail, and it prints all the license and all, and then finally it makes the shell ready for you. So this is how we invoke the Opentimer shell, and finally after printing out, the shell becomes ready here. Not only Opentimer, all the industry standard STA tool are command line. They have the same look and feel as Opentimer. So folks, when you are learning the Opentimer, you are getting ready for the industry standard STA tools, and you are moving one step forward. We are done with this particular slide. Let's move on. STA command example. You have seen the flowchart few slides back. Now let me exemplify the STA commands according to the flowchart. Here goes our example commands. First, include all the libraries, technology and IP model libraries. We start with a set command, set link path, and then star.db. Then we read all the gate level design files. The read verilog command, so then we have a verilog file here, fullchip.b, which is processed by the read verilog command. Next, we read libraries and link the design with the link design command, and then we give the fullchip, the design name. And then we read the SDF file. So with the read SDF file and the respective arguments, we read the SDF file. Next, we do all sort of reporting. Report design, report clock, report annotated delay, report annotated check, check timing, and etc. This example is from industry standard STA tools. That could be any. Common structure is very same. And we are done with this particular slide. So let's move on. Opentimer command example. Now let me introduce you to the Opentimer commands as per the STA flowchart. You will find resemblance with the example in previous slide. So here is our placeholder, and we start. Include all libraries including timing model. Read celllib mycelllib.lib and read all the gate level design files. Read verilog mydesign.v. Then read the spef. Read spef, then mydesign.spef. This particular spef file comes after the post layout. That means once the layout is ready. I have made already an episode on spef. In case you have seen, it's good. In case you have not seen, go ahead and see that episode. Next, we read the SDC file. Read SDC, then mydesign sdc.sdc. Then do all kind of reporting. First, we do the report timing. Then we do report leakage power. Then we report AT, that is arrival time. Then we do report RAT, that is required arrival time. Then we do report slew, then report slack, report area, and so on. So all of these commands mentioned here, you have to source them one by one in the Opentimer shell. And folks, you have a good opportunity to install the Opentimer and try this. We are done with this particular slide, so let's move on. Why we do report timing? The report timing command is to get the STA report. This is common to all STA tools including Opentimer. Let me show you the reasons for using the report timing. Default, it returns the worst path for max analysis for each clock, recovery check, clock getting checks, so all sort of these checks. Next, customize with many different switches. Setup versus hold reports. Increase the significant digits. Focus on specific paths. Increase the number of generated reports. Include net fanout. Expand the calculated clock network delay. So you can see you have the basic kind of reports first, then you can do playing around with multiple commands and fetch multiple other data from the shell. Over time and continuous development, more things may get included in report timing command. So always consult the latest STA tool manual. Only a latest manual can give you the right set of commands that are applicable in the STA shell. We are done with this particular slide. So let's move on. report analysis and you. Any guess why I have kept this slide? Let me tell you with a couple of infographics. Suppose there are 170 violations that have been reported after you run the report timing analysis in actual practice. I'm talking about the real-time designs when you do the reporting. And obviously when we are dealing with the Opentimer test cases, we don't see this amount of huge violations. In real world and real practice, huge violations will come because the design is a multi-million gate structure. Now, when 170 violations are reported, what we see? What we look for, what else is there apart from violation? Is there any other information? This is case by case and you have to be very observative so that you can pick up things from the report. Are all violations real? Now, why I am pointing this particular question? Because when I have discussed the theories, I have mentioned there are many false errors that are flagged by the STA engine. I'll not repeat the names. I have already explained them in the theoretical episodes. And all these false alarms can come inside this violation. So you have to root out all these kind of false alarm from the actual violation. So first you have to segregate the false alarm and keep the actual violations. So that will reduce some amount of number. Can you explain warnings in the log file? When you run the STA engine, there will be certainly some log files generated, or when you are running in the shell, there will be some amount of logging data thrown in the screen. Does it help you at all? In case you are running a shell and there a log file is not generated, you can use a tcl command to open a file and dump whatever coming out in stdin. So that way you can customly create a log file. How to write file, open file, everything I have already discussed in the tcl episodes. What are the action items for resolution? Now, when you have browsed through the 3 above points, what else is there, what all violations are real or not, you have got any errors and warnings in the log file, and then what are the action items for our resolution? Now you have all the data, everything you have analyzed. Now you are thinking what we should do for the resolution. This can be multiple things, whether you have to do some changes in your RTL or you have to do run some what if analysis so that you can check within the shell. We'll come later on this what if then analysis. We have some feature in Opentimer. I'll come to that. So all this sort of resolution you have to take. Next is the special situation. What are the issues? Now, why I have kept this part or this question is that there will be certainly design specific and some special error or warnings or violations, rather be more specific. On those cases, you have to think deeply and take action. Timing report, that is the report timing command. The purpose of this slide is to make you familiar with the STA timing report. So let's begin. Once we run the report timing command, after the initial few steps that shown in the flowchart, when we hit the report timing command, this kind of report is generated by any STA tool. So this is a common structure, and here you can see there are different sections. Let me one by one tell you the sections. This is a header section. Here is my mouse pointer. You can see the start point is FF1 and the end point is FF2. Path group is clock and path type is max. So I'll come what is this max analysis later on. So this is the header section. Next, we have the data arrival. So this entire section captures the data arrival, and here you can see this is the data arrival time. This is AT. We have discussed so many times AT RAT. Here it is the AT, and here the AT value is there. So all these arrival times are summed up, and here the total AT is calculated. So this is the data required time. Here this sections gives the data required time, that is RAT. So RAT, whenever we sum up all these things and we get the RAT here, this is the RAT value. Finally, we have the difference between the AT-RAT, and that is showed as slack. Later, I will show you the slack equations when I give the explicit example. There I will define the slack equation also. The section here, you will get the slack, where you can see that whether it is met or violated. In general, the STA, the report timing, whenever you run, is a short and sweet version, but the report can be long, more than that. But generally, there are 4 sections. First is header, then the arrival, then the required, then the slack. So even there could be multiple such paths are reported, and all these reports will be there one by one after another, reported once you hit the report timing. This structure is more or less same in all the STA tool. Here in the last section, you have visualized the AT-RAT in real time. We are done with this particular slide, so let's move on. OpenTimer commands. In the upcoming sections, we will go through all the OpenTimer commands. You have to memorize most of them when playing with the STA report and further analysis in the command line. So fasten your seatbelt and start the high-speed journey in this section. OpenTimer license. OpenTimer is a free and open source software. You can freely use it under the MIT license. So enjoy. Commands to read the input files. These are the must-used command except the update timing. You have to use all others every now and then. Let me bring my mouse to describe these. So here first command is read cell leave. Here we can see min max. These are for respective delay calculation, and here we give the cell leave, the timing library name. So this reads the timing library. Example is read cell leave library.lib. Then the read verilog. Argument is file name and it reads the verilog netlist. Example is read verilog then design.b. Then comes the read spef. Argument is only the file name. It reads the R, C and CC information from the spef file. So read spef, then design.spef is the usage. Read SDC, and here the argument is only the file name. Read design constraint file, and the usage is read SDC then constraints.sdc. And we have some update timing. So suppose we have updated anything like verilog or spef in between the timing engine, and then we have to hit the update timing. So it will update the timing according to the updated file. Or we have done some what if then changes, and accordingly we have to update the timing internally. So for that purpose we have to use the update timing. So this is update timing. Usage is just the command you have to type update_timing. That's all. So we are done with this particular slide. So let's move on. Report timing command. This is the most important command in STA. Without this, you cannot do the analysis. Where is my mouse pointer? The command is report timing. Then we have number of paths. We can put an integer how many paths we want the reports. So it means the number of paths to report. Then we have min, the mean path analysis. The max is the max path analysis. Then we have rise and fall, the rising endpoint and the falling endpoint. So these are all arguments and the purposes. Now let me tell you some more facts about this command. If the num paths is unspecified, the OpenTimer report the most critical path. If both min and max unspecified, OpenTimer report the critical paths across both plates. If both rise and fall are unspecified, OpenTimer report the critical paths across both the transitions. That's all folks. We are done and let's move on. More reporting commands. Let me introduce you to some more important reporting commands. So here it is report TNNs. It do not have any arguments. That's why you have not applicable here. Report the total negative slack, and we directly use this command without any argument. Then report WNS is the report post negative slack. We use the command like report_WNS. And then we have the dump graph. Then -o, then file name. Dump the timing graph in a DOT format, and it is dump graph. And then dump timer, then file name, and dump the design statistics, and then the timer. So we will later on show the example, so don't worry. We are done with this particular slide, so let's move on. Some more reporting commands. The list has not exhausted, folks. Here, these are only commands you have to use. To enable CRPR, enables the common path pessimism removal analysis. This triggers path-based timing update and can increase the runtime. After this enable, if we want to disable it, we use the disable CRPR. Disables the common path pessimism removal analysis and adopts only the graph-based analysis. So report TNS, report WNS we have already covered, but somehow I have kept it in this slide. So again I am telling. So report TNS is report total negative slack, and report WNS is report post negative slack in the design. Report FTP reports the total failing endpoints of the design. And finally the report leakage power reports the aggregate cell leakage power in the design. So these are the commands. You can use them as is, and all these are purposes. As you have come across all these reporting command section, now you are realizing what the power the STA tool has. So we are done with this particular slide. So let's move on. Report Slew command. As the name suggests, we can do more with this particular command. Let us see how. So here This is my mouse pointer. This is our command and all these are arguments. So pin name gives the name of the pin for which we are doing the query. So these are kind of query command, and min the minimum transition time, max is the max transition time, rise is the transition time at the rising edge, and fall is the transition time at the falling edge. So this way we can use the report slew command to report the slew of a pin, and this is one of the command which accesses the design database. So when all the database separate files are joined and stick together inside the shell, from there you want to pull out some data. This is one of the command which you can use to pull out some data. Report slew command of a particular pin. We are done with this particular slide, so let's move on. Report slack command. We can play with the slack with this particular Swiss Army knife. Let me show you how. Here is my mouse pointer. Report slack is the command and all these are arguments. Pin gives the pin name on which we want to do the query. Min is the minimum slack time, max is the maximum slack time, rise is the slack time at the rising edge, and fall is the slack time at the falling edge. So this way we can do the slack query. We can use it to determine slack at various pins. Okay, we're done with this particular slide, so let's move on. Report and dump commands. We will conclude the report and dump commands with this particular slide, and here we go. So here we can see that there is a report area. This is a command and you can use as is. The report area, this reports the aggregate cell areas in the design. Dump timer, the output shows the summary of the design time, number of pins, number of nets, units, and so on. So this gives a summary. Dump task flow dumps the present lineage graph of a DOT format, and dump graph dumps the present timing graph into a dot format. These are two particular commands which gives the output in a DOT file format as output. We can visualize the dumped graph using this online tool. This tool can export the graph in picture format with SVG file extension. The link is also provided in the description so that you can access the online graph visualization tool once you dump some graphs from the Opentimer shell. We are done with this particular slide, so let's move on. Design manipulation commands. Sometimes we have to do some what if then situation analysis which will reduce some actual design manipulation time, and hence the total turnaround time also be very less. Since the whole design is loaded into the shell, you can manipulate the design live inside the shell without going back to the RTL code. Now, let me go through the commands one by one. First, this command is insert gate and its argument is gate name and cell name. The names of the gate and name for this insertion command. Remove gate name. The name of the gate to remove from the design. Repower gate name then cell name. The names of the gate and the cell for repower operation. Insert net name. Only the one argument. The names of the net to insert into the design. Remove net name. The name of the net to remove from the design. Then connect pin name then net name. The names of the pin and the net to enable this connection. And disconnect pin name. The names of the pin to enable this disconnection. Now folks, you can see all these are kind of what is then situation analysis commands, and if you remember we have talked about the update timing command, so that will be used in conjunction with all of these commands. Once you do these all kind of changes, you have to update the timing inside your shell. So folks, I am done with this particular slide and let's move on to the next slide. General config commands. We can configure units using these commands. You can see the command is set units. Here is my mouse pointer. Time then unit. We can play with the time unit. Capacitance then unit. Capacitance unit is farad. So here all the default units are mentioned. Then resistance unit, then voltage then unit, current then unit, and power then unit. So we can change the unit if we want to do. Whatever unit we want to represent the outcoming data, we can change the unit as per this. So all we can play along all the units with this particular command. So we are done with this particular slide. So let's move on. Timing config commands. We can configure arrival time and required arrival time with the help of this command. Where is my mouse pointer? The two commands are there. Set AT, that is set arrival time, and set RAT is the set required arrival time. Both has the same style of the arguments. Both are applicable. Pin name gives the name of the input port pin. Delay, the arrival time value. Mean, the minimum arrival time. Max is the maximum arrival time. Then rise, the arrival time in rising edge. And fall, the arrival time at the falling edge. Either of these two commands can be used with the same arguments. And the meanings are also same. So these two can be used for playing around with the AT-RAT in the circuit. We are done with this particular slide. Let's move on. Slew config command. We can play with the slew using this command. Let me describe how. Here is my mouse pointer. Here the set slew command is there, and you can see all the arguments are in this column and the purpose is in this column. So here pin, then name, the name of the input port pin on which we are setting the slew, then the slew value, the input transition time value, min, the minimum transition time, max, the maximum transition time, rise, the transition time at the rising edge, fall, the transition time at the falling edge. I think these are very straightforward in meaning. So we are done with this particular slide. So let's move on. Load config command. We can play with the load values with this particular command. This is how we do it. Here is my mouse pointer. This is the command set load. This column gives the all arguments. These are the purposes. So pin name, the name of the input pin. Load, it is the load capacitance value, and min is the minimum load capacitance. Max is the maximum load capacitance. Rise is the load capacitance at the rising edge, and fall is the load capacitance at the falling edge. So these are very straightforward in meaning. And one thing, folks, in timing analysis, when we are dealing with load, by load we mean always the capacitance. We do not mean any other thing. So keep this pinned in your mind. We're done with this particular slide. So let's move on. Opentimer example. In upcoming section, we will explore one Opentimer example test case. You will know how to run a STA test case inside the Opentimer shell. You are now familiar with all of the Opentimer commands. So this will be very easy going for you for this next section. Opentimer example. This is the circuit diagram of the design under test. This is a very simple design to understand. We will use the Opentimer shell to load the design in the following way. Let me bring my mouse pointer to explain. Here you source the Opentimer shell. This is basically the area where you have compiled the Opentimer. Here you can go and open the shell. So this is the Opentimer shell. This is the area where you have compiled the Opentimer. There will be a bin directory. Inside there will be OT shell. So you can use in this way, or you can use in the another way that I have described in the installation video. So once you source the Opentimer shell, you get this kind of header printout, and then the shell is ready. Once the shell is ready and you are inside the directory where the example is there, what you will see? So you will see differently Verilog SDC file. So these three files will be there. So we use the read cell lib to read the lib, then the Verilog, read Verilog to read the Verilog, and read SDC to read the SDC. And then we will reheat the report timing to generate the report. This is a simple example. The test case name is also simple. You can get the test cases in the same GitHub link from where you are downloading the Opentimer. So there these examples are there. I think when you download the entire thing, the test case also come. Otherwise you can download from the GitHub. We are done with this particular slide, so let's move on. I mentioned that at some later time point I'll clarify the max and mean analysis. So here you can see the setup violation comes under the max analysis, and this max, why this is max analysis, you will see. In this slide we will explore how to catch the setup violation in Opentimer STA. This is our design. We are interested in this path for the setup violation. We run the report timing command with the max option, which is used for detecting the setup violation. You can see the report has how to analyze the setup violation and be sure that this is a setup violation. This is a very good question. To do so, we depend on the slack value. For the setup to be proper, that is, there is no violation, the RAT minus AT must be greater than or equal to 0 as shown in the equation I have just displayed. Now, where is the AT, that is arrival time, in the report? When we add all the delay values from clock pin of the flip-flop up to the output pin of U3 from the diagram, we get the total arrival time. You can relate the path in the rightmost column. Let me bring my mouse pointer. So we are talking about this path, clock, then Q, then U2, U3. You can see this is clock, then Q, then U2, U3, U3, U3. Okay, so this is the path through which the data is coming. So these all adds up to this value. This is the data arrival time. You can see here. And here you can see this is the RAT, that is required arrival time. Here it is reported as data required time. So that means required arrival time. This is RAT. You can see the arrival time is greater than the required arrival time. That is AT is greater than RAT. So the slack is violated as per the equation. You can see here, if we go down right, here we can see that here it is negative and here it directly flags that it is violated. So that's why I have kept all these lines in red so that you can distinguish from others, and here you can see it is violated. And here another thing I would like to mention, this max is there, but this bracket I have kept for you to understand. It doesn't go in the actual command. And here you see that start point and the end point, PLK and the out. Here we derive the final conclusion. Max path analysis refers to setup time analysis. The data arrived at in out much later time. The value is given in bracket, that is 10.724 than expected. Hence, the setup time at clock in, that is F1 colon clock to out, is violated. Here the arrival time is much greater than the required arrival time. One more thing to say here, that this path is a range to output kind of path. If you recall, there are four types of paths on which we do the static timing analysis. This is one of them, and this is the range to output path. We are done with this particular slide, so let's move on. Hold violations, mean analysis. In this slide, we will explore how to catch hold violation in Opentimer STA. This is our design under consideration. We are interested in this particular path for hold violation. We run the report timing command with mean option to trace the hold violation. You can see that the report has come how to analyze the hold violation and be sure that this is a hold violation. To do so, we depend on the slack value. For hold to be proper, there is no violation. AT, that is arrival time, minus RAT, that is required arrival time, must be greater than or equal to 0 as shown in the equation. Now, where is the AT, that is the arrival time inside the report? When we add all the delay values from input port of E1 up to the D pin of the flip-flop in the diagram, we get the total arrival time. You can relate the path in the rightmost column. Let me bring my mouse pointer to show you. Here is input pin, that is here. Then this is E1, we are crossing E1. Then U4 is here. And finally we reach the pin D here of the flip-flop. So this is the path that the data is traversing and arriving. This is the data arrival time. And this is the data required time. You can see here, I am pointing my mouse. So the slack is violated as per the equation. You can see the hold failing text has come also here. So in Opentimer, here we can see it is already reporting the hold failing. This hold failing flag is already there. We see the slack is violated. So this slack is calculated as per this flag. Okay, it don't have a fixed meaning, and this particular slack is calculated this particular equation, and that is linked with this mean or max analysis. Okay, here it is violated. The hold violation is just saying right now. How we derive the final conclusion? Mean path analysis refers to hold time analysis. The data transition at F1 colon D was required to happen after time 26.518, whereas its transition occurred way before at time 2.967. Hence, it causes a hold violation. Here, the arrival time is much less than the required arrival time. This path is of type input to reg. As you know, there are 4 types of path on which we do the STA analysis. One we have seen in the last slide, that is reg to out, and this is input to reg. We are done with this particular slide. Let's move on. Checking summary and units. So when you have a design, you want to have the different counts, right? What are the different counts of nets, gates, etc. This command, the report timer command, this is how we get the gate or net count time summary, and as well as the units, whatever we are using the units. While you are reporting the units here. Sometime back we have seen there is a command with which you can change the unit on the go inside the live shell. Then how will determine what is the unit? So this command will print out the unit. As well as here you can see, let me bring my mouse pointer. Here you can see number of pins, gates, nets, cells, all these are reported. So this gives a short report. You may require it for unit change, you obviously require it, or there is a what if then analysis you are doing, again you will need it. So I think we are done with this particular slide. Let's move on. Hey guys, welcome to the 11th episode of Static Timing Analysis. Today onwards, we will do hands-on static timing analysis using the Opentimer STA tool. In VLSI, when you learn any software hands-on, you have to stack the corresponding theories in back of your mind. In last 10 episodes, we have covered all the theories and some amount of STA commands. So now we are ready to play with the STA tool on VLSI test cases. Stay tuned till the end of this episode for hands-on knowledge using Opentimer STA tool. Hey guys, welcome back. We are in our computer now and this is the menu for today's episode. First, we will do the cloning of Opentimer test case into our local directory. Tour of various files inside the test case. Opentimer alias creation for easy use. Hands-on design loading in Opentimer. Hands-on report timing command for various of its switches like mean, max, rise, fall. Then hands-on example of report FEP, report TNS, report WNS, etc. Then we'll do the hands-on on report slack command for its various switches like mean, max, rise, fall, etc. So this is a very consolidated menu for today. So without any further delay, let's begin the hands-on practice using the Opentimer STA tool. So folks, as we have discussed that we will clone the Opentimer test cases from its GitHub link local to our directory. So let's first go to the Opentimer GitHub URL. So I am typing in Google. So Opentimer STA. Once I click here, I get the first link as the Opentimer URL. Now this URL I am providing in the description. You also can pick it up from the description. So here, once you open, right, you can see there is a folder called example. This is clickable. So once we click it, we go up to the subdirectory here, you can see. So we need this particular directory to go inside and we'll start our hands-on practice using the simple test case. And once we click the simple subdirectory, right, we can see we have gone up to this much of depth. So we want to clone this simple test case and all of these files here in the test case into our local directory. So how we do that? So we go to our terminal and I have created a directory here for Opentimer test case in my hard drive. So there I am using ghclone. So the installation of the gh binary is also given in the description. So you can pick it up from there. It's very easy to use. So what we do here, first we type ghclone and then we give the URL. So URL is here, right? Here we can use the Control A to select all and then Control C to copy, and then we here and click our middle mouse button. So this is the command for copying the simple test case from this particular URL locally to our hard drive. So let me hit the enter. So it started cloning the simple test cases and all the files. It's showing it's done. So let me do a ls. So here I can see the folder simple that has been cloned into my local hard drive. Now this cloning term is very much specific to GitHub. It is similar to copy. The copy, the cp command that you use in your Linux system or Unix system. Since you are downloading from the GitHub repository into your local hard disk, we are using the term cloning, and hence the binary is also named as gh-clone. One more thing I would like to tell you that I have given all the description and the install instruction of Opentimer and all the necessary dependencies, even for the gh-clone, everything in the description, so you can find it out there. So now let me go inside the directory. I hit the tab and I am here. Let me do a ls. Okay, so here I can see there are a lot of files here. This is how the test case has been created by the Opentimer team. So let me open one by one. So I am using my gvim alias to G, and hence I am using my alias. So you can see which G gives me the gvim. Okay, so I am using gvim here. Just I am opening the Verilog file. So you can see here, first we have the module here, the module name, and then we have a set of inputs and outputs defined for this particular module, and we have all the nets, that is wire connection here, and here we have the instances. Now you are asking from where they are coming. If I go here and we go to Opentimer, and there if we scroll down right, here you can see this is a simple test case timing report example on a sequential circuit design. The description is this, and the library is OSU free PDK 45 nanometer. If I hover my mouse pointer over it, you can see the link from where this PDK belongs to. It's a 45 nanometer PDK, and you can also go into the URL if you want to explore it. And we are using this simple test case. So now let's come back to here in the gvim. So all these cells are belonging to this 45 nanometer PDK. So from there we have got all these cells. Now let me close this particular file. Now let me open the next one, that is the SDC file. So here you can see the SDC file have been opened, and you can see that I have already in the SDC file episode, I have described what are the contents inside the SDC file and how these design constraints are written and what they mean. In case you have not watched the episode, please go ahead and see that episode. Here you can see that there is a create clock. Clock is created. Then we have specified the input delay. We have used max and min branches and rise and fall splits, and we have for ports we have used, and we have also used the clock. So we have used the delay and the time unit. We have time unit can be seen when we report all these units inside the Opentimer shell. You can get the timing units there. And here also, now this is the delay. Now we have set all the transitions here. You can see all the transitions here has been set for the min max and as well as their rise and fall splits. So here are the ports and here are the clocks. Okay. So we have also put the load here, and output delay also specified. So all these design constraints have been specified in the SDC file. So you can learn more about in the episode where I have discussed about the SDC file. So we are done with this particular file. So let's close it. So next file is the lib file. So this is the timing lib file. Let me turn off the highlight. Here I have closed the highlighting. Otherwise it is very tough to see. And you can see, for going ahead or telling anything, I have also created episode on how to read and how to interpret the timing library for STA and what all the things you get there and what are their meanings. Please watch that episode in case you have not watched. So here is the timing library for that particular PDK. And if we see, here is a particular header section where all these threshold, PCT rise, PCT fall, etc., and norm process, norm voltage, norm temperature, and operating condition, that is PVT, is also defined here. PVT is defined. So you can see here all the LU table template are here. And then once we cross this section, then we have cell. And here, if I just go, this is a cell end again. In GVim, I have used shift 10% for the matching curly braces. So again, here there is another cell, and if I go down, here we can see different pins are there and all the LUTs are there. So you can interpret this particular timing library. Now, all these files will be going inside the Opentimer shell once we invoke it and once we source it. Rest of the files are a couple of configuration files are there, that is internal and maybe specific to the Opentimer. You can explore them by yourself. In case you have a question, you can put it down. Just one thing I would like to show you here. Here it's the timing file. Here there are some internal formats of Opentimer by which the AT, RAT, Slew, etc. and the clock is defined. All these things have been defined for this particular test case. And I think CPP file we will not talk about right now, because the CPP is for the API sections, and we are doing here very much simple analysis using the shell. At some later point, we may look into the CPP and explore that particular side. Right now, we will be focusing on the basic example. Now, here is the simple.conf. Conf is nothing but it gives a shortcut of all the commands that we use. Generally, here you can see all the commands sequentially they have mentioned in the conf file. So basically, we can do it by hand once we turn on the shell. So now at this point, two things we are done. First, we have done the cloning of the test case. Second thing, we have made ourselves familiar with all of the files inside the test case, and also we know from which PDK all these cells have come. So here I would like to turn on the Opentimer shell. Now there is a good point that Opentimer, I have created the alias. So let me invoke the alias. So when I do the which Opentimer in my shell, I can see that the Opentimer command is alias to this. So when I grab the CSHRC file and the text I am grabbing is Opentimer, what I get? The alias. So alias Opentimer, and this is the thing. Here the path of this. And how you set the path, all these things I have given in the description. So please check it out. This has also been told in the installation of Opentimer. There also I have mentioned. This is for the CSH cell or TCSH cell. In case you are using the bash, this alias command will be changed. And I think you can find it once you Google it, how to do the alias in the bash. We are done up to this point. Now let me clear the screen. We are now cleaned. Now, so here we are now. Let me hit the Opentimer. So here I have typed the Opentimer. Let me do the ls. ls gives all the files here. So one good thing of this shell is that if you type right and if you hit tab, the commands get completed. Let me show you how. So once I type read and then I hit the underscore, what I get, that all the commands I am getting. Okay. First, I'll read the lib file. Read cell lib, and then I give the cell lib name here. Okay. And the first thing is done. The next thing is that what we do is we read Verilog file. Read Verilog, and then we have the Verilog simple.b. We read the Verilog. Then we are using the read SDC. So I'm copying the commands from here and copying the file from here. Read timing. Okay. So read timing and then simple.timing. So I think all these files are done. Reading and internal loading of the files is done. Now let me do the report timing. Here once I doing the report timing, right, I am not giving any of the arguments at the beginning, and let me see what happens. So what you can see, that it has read the Verilog, then it has read the timing, and all this timing I have shown this file also, some few simple settings for this tool, and then loaded the SDC and then the lib, all these things, and you can see the units are here, and finally here it is giving this particular output. Now we are getting only one output. If we want to get all the outputs, so here let me bring up the report command. First let me clear the screen and we go back to the beginning, and here let me invoke the report timing command, and here this is num underscore path, and I hit 10. So here we can see a huge number of violations are coming. You know right that the max is for the setup violation and mean for the hold violation. If you can see here, it is mean violation and here is hold failing. I have already explained in the last episode, and here you can see again this is mean and it is hold failing. Now if I scroll down right, also there are more mean violation means hold violation are there. There is also max, that is setup violation. So you can see here. Now if I want to just segregate the hold violations, let me clear the screen here, and here my screen is clear again. Let me push the up arrow of my keyboard, and here the report timing commands come, and what I have to do, I have to do the max analysis for the hold violations only. So this will provide only the hold violations. So once I type in, right, you can see the hold violations, that is the max violations are reported. So here, how to analyze this particular report, I have already explained in last episode. So please watch that episode to interpret this one. And you can see here, it is also the max is coming. So here you can see there are, the start point is F1:CLK and the final is out. So this is clock to out this path. So that is a basically rage to output path. So here you can see the difference lying in this particular column. So direction, that is fall, rise. Okay. So here this is the direction based on which the difference in the slack is coming. Okay. The slack is here minus 10.724 and here is 10.042. So the difference is in this particular column. Because of the path is same, F1 colon CLK2 out, and here is also the same path is there. Variation of the rise and fall transition. Say if we are considering this fall, then rise, and then finally we are having considering fall. So here you can see that combination is different, and because of this we are getting the particular difference in the slack. Now my question is, we have this, and then what if I want to segregate one level down? What I have to do? So let me clear the screen. We are again at the top, and here max, and then if I give the rise, okay, and I hit enter, so the rise split is displayed, and if I give the fall, the fall split is defined. You can see that here the two slacks are different for the rise and fall split. So this way we can further narrow down or do the filtering of hold violation or setup violation. In this case we are doing the max, that is setup violation. And now let me go for the hold violation. Okay, so let me clear the screen. I hit clear. The screen is cleared. Now let me erase these things and give min. So here once I hit the min, what I see that there are a lot of 1, 2, 3, 4 hold violations are there. The 4 hold violations are there here, and obviously these are the worst cases of violations. When we talk about, these are the pessimistic cases on which we are getting the violation. Now if I want to split the rise and fall category, right, what I do, let me clear. I have done the clear of this particular screen, and let me bring up that particular. Okay, now here we add rise. So here once we do the rise, right, we can see that 2 categories of rise split here. For the hold violation, in the rise split we have 2 violations here, and if we give, let me clear the screen again, and let me bring it, and in case of fall, we are getting how much? So again 2 are there. Okay, so for the fall split also we have 2 violations. So you can compare these columns for one particular category, right, for the fall or rise split. Okay, fall, rise, fall, rise, fall. Okay, and finally the fall. But in case both are similar, the directions are similar, right? And in case we had the rise, what we see here, if we see rise, fall, rise, and rise, fall, rise. So their transition directions also same. So these 2 are coming in the rise split, and these 2 are coming in the fall split. So this way you can also see that different branching outs of the violations in cases when there is a rise transition, when there is a fall transition, right? During the entire series, during the theoretical explanation, during the timing lead chapter or episode, I have mentioned that there are various rise and fall conditions. So the rise and fall delay and slew, etc. may not be same, may be same. So there could be different cases, and here you can actually see where these particular things get impacted. So this is kind of a hands-on experience on using the Opentimer. So we are done for the report timing command for now, and for this test case, let's move on to the next examples. I'm clearing the screen here, and let me do the report I hit report and I hit tab. Okay. So here so many report commands are there. Let me see what we are getting here. First, I am interested how much area will this design will cost. So I am saying we can get the units, area units, get it from the dumping the units. I have already shown that in last episode. I think in the last slide I have shown how to dump the units. And here the report area is 176. Now I think the dump command is dump timer. Yes, the dump timer gives is the units. So here you can see all these units. Okay, whatever is there. So now let me clear the screen, and I am hitting the report again. So there are so many report commands available here. What you can do, we can print different report commands here. Report area. So where is report TNS? We are reporting the TNS here, and if I hit the report WNS, it gives the WNS. Report FEP. So I have already given the description all these commands. I am not elaborating them, otherwise this will become much more lengthy. Want to make it very crisp. That's why I am doing short and sweet things. So the report RAT. Okay, so you have to give the pin name. Not now, we will do it later. So these things, and now let me do the report slack. Report slack. Also, we have to give the pin name. So let me do the report timing first to get the pins. So here simply we are getting one here. Let me put the report slack here, and then dash pin. Here let me give about this pin. Okay, this particular pin I am picking up and giving it. So here the slack is -22.2. So even now if we want to go further down in the max, mean or rise fall, okay, we can go further. So if I give the max, so it will give the max. You can see the max here, and if we give the mean, we can get the mean slack. Okay, so whatever we are getting the here, it's the mean slack. So mean slack means because we are having the analysis type mean and we are getting the slack. So once I reported first, right, it gave the mean one. But in case you want to see the max, you can see that. Now let me add more switches. So for mean, if I want to give rise, for fall we have a different. So for rise one thing we have, for fall we one thing have. So this way we can go every pin by pin and get their slack. So this way we can do the analysis. Now let me give some more example using this report slack command, and here so pin, let me what is coming in the output. So here although we are seeing the path from input to F1:D, but if I give report slack, it's not dependent upon this report, but that's why I became curious and I wanted to see what is coming in the output pin, out pin. So here we can see this. Now if I want to vary it, max is coming as 10, Mean is coming as 20, and then we can go for rise 20, fall 20.7. So here we want to report the slack in each and every branches. So mean max analysis and then rise fall split. So we can do any type of combination and find out the slack of that particular pin. I think we are done with today's example, and in next we'll do some more experiments. We'll explore some more commands. So we are done for today. Hey guys, welcome to the 12th episode of Static Timing Analysis. We are continuing hands-on practical using the Opentimer STA. Today, we will dive into the design data analysis to Opentimer STA, where we will focus on two different modes of analysis. First one is based on the single pin instance data, and the second one is consolidated design data for the entire design. Stay tuned till the end of this episode for enhancing your knowledge on hands-on static timing analysis. Hey guys, welcome back. In today's episode, we are going to discuss these points: reporting overall failing endpoints, reporting overall leakage power, pin-wise reporting of slew, slack, AT, RAT, consolidated reporting of slew, slack, AT and RAT, consolidated reporting of pin capacitance, consolidated reporting of net load, consolidated reporting versus pin-wise reporting, side-by-side comparison. That's the menu for today. So without any further delay, let's begin. Hey folks, we are back in our terminal, and here we are doing the experiments for today. So let's begin. So these are the files. I am using the same test case as the last hands-on session. I am invoking the Opentimer. The Opentimer shell has opened. Now let me clear the screen. Let me do a fresh ls. So these are the file. Now I will load the file. First I load the library file .lib. Then I load the Verilog file. Then I load the SDC file, and then I load the timing file. I have loaded all the files. Now let me do the report timing. Now you can see that once I hit the report timing, all the things get processed one after another. So even if I load the files and don't do the report timing, the internal timing analysis process will not happen. That process has happened. So when it is happened, first time you can see there is a log created, as you can see in this section, right? And then you can see that there is a section here that is reported one particular path for the timing violation. So let me clear. And now I will begin the experiment about accessing the design data. Now there are two sides of the design data. First thing is that you have the design component, the pins, the cells, and the cells will have slew, load, etc. So this is one kind of design data. This comes as the input design data or the structural design data. Now there is another set of kind of design data, which is the output. That is when you are simulating the circuit will give some output. Those kind of data is like the timing. Already we have done the report timing and many other reporting. So one of the reporting is failing endpoint. So you can see the which endpoints are failing for the timing, and you can report the leakage power. So first let me try out the failing point. How many nodes are failing? So let me hit the report and then hit tab here. So you can see here is the report failing endpoint. So this is very straight and simple. So when I hit, it gives the 4. The next one, the design data, that is the post simulation data, and the post one is the report leakage power. So if you can see, the leakage power has been reported here. There is another type of reporting that is much more structural. Now we will enter into that domain. First we'll do the pin by pin reporting and then we'll go overall entire design wise dumping. So first we'll start the pin by pin reporting. I'll pick one particular pin and on that pin I will iterate, because when we are in the static timing analysis, we come across the theories about the static timing analysis, and here in the shell when we are doing the analysis. The analysis will be done by you and you have to do the debug of the issues, and for that particular purpose you have to know how you can proceed node by node and pin by pin. So theoretically, what I mean that node by node, you have to go forward or backward in a particular timing path, and then you have to analyze where the subject to change can happen. How we are changing, I'm not discussing in this episode. But you must know how to proceed and traverse inside a timing path so that you can pick up the points where you can make the changes to wave off the violations. Now here, when we are having this path here, the path, you can see the path starts from input 1 and the path goes up to F1:D. So this is the input port and it is the data pin of the flip-flop. So let me pick this data pin of the flip-flop for our analysis. You can pick up any point. Here you can see the rightmost column here. I'm hovering my mouse pointer. So here you can see at the rightmost column, all the pins are there. Corresponding cells are also there. You can pick any one of them when you are practicing. First, let me print out the slew. So I give the command report slew and then pin. Now it has given one value, but generally when we are getting, we will have 4 combinations. Okay, let me demonstrate you. Main here. Now if I process further, you can see this is the mean plus rise combination. If I change it to fall, we can see the value changes. Now let me change min to max. So here I'm giving the rise, you can see here, and then I'm giving fall. So you can see there are 4 branches. These 4 branches have different branches, I mean to say the branches of this particular command, not your timing path branches. So here you can see the first value, the second value, the third value and the fourth value. So there are 4 set of values. And in last episode, I have shown you that based on this particular column, you may get a difference in the reporting values or the different slacks. Because based on which particular transition you are picking, the rise transition or the fall transition, and the type of analysis, whether you are doing a mean analysis or the max analysis, that actually invokes different values, because they are physically different values from the particular gate or their pins or their rise and slew condition, which actually are picked up from the .lib file. Mean is our hold violation and the max is the setup violation. At command line, we are using mean and max, so we are not every time saying hold or setup, but rather than min max, because we are traversing using the switches. So here we are done with particular the slew experiment here. Let me clear the screen. I keep the pin fixed and I vary the commands. Report slack. Then I give the pin and then I am writing F1:D. So here I just initiated another set of command how to report the slack of the pin. Now when I am experimenting and exemplifying this to you for one particular pin, it doesn't mean that you will stick to one particular pin. You can move to and fro inside a timing path from start to big end. So there you can analyze by your own. So here I give the min with rise. So you can see that this value was already printed. Now changes to fall. The value changed. Now I change max and then rise. Again you can see the value has changed. And here max with fall. So you can see if I am querying the slack of that particular pin, which is the data pin of the flip-flop, I can see that different slacks are reported based on the type of analysis, that is min or max we are choosing, and the corresponding transition rise or fall we are choosing. So accordingly all these values will be printed out. And in case you have no idea that how this value is coming, I have created one Tickle episode, the first episode of Tickle, how Tickle APIs work. There I have explained with infographics so that you can understand. So do watch that episode. I am providing the link in the description. Now we are done with the report slack command. Now for the same pin, what we will do, we will report AT, that is arrival time, for pin F1 colon D. Here we just print it. Now we will proceed further again for the min and rise. You can see that this particular value was only reported when we have given no further switches. So now again we change the rise to fall. The value changed, the AT changed. Here again when I changed, it's different from the previous two values. Here I am giving the fall, so you can see. Now let me bring my mouse here. So first value, second value, third value and the fourth value, each are different from one another. They may be close, I am not talking about that, but the numerical value, they are distinctively different from each other. So this way you can pick a particular pin. Now I am making the pin constant here and I am varying the analysis type, that is report slack, report AT. When you are analyzing a timing path, your analysis type will remain fixed and you will traverse along the path, thus changing the pins. So this is the only difference. The next is report RAT in F1 column D. This is the RAT that is by default coming. Let me add the switches now. So this is the min plus rise combination. The min plus fall. So when I am bringing back the commands, I am using my up arrow in my keyboard to bring the command back. So here it is the max plus rise combination, and now I see the max plus fall condition. Here you can see So you can see that here first, second, third and fourth. These two values are close enough. These two values are close enough. But since the mean and max are the two different analysis types, so these two are far apart. So the values of mean, they can be very near to each other, and the max, they can be near to each other. But the max is very far from the mean analysis type. And numerically each value is different here, whichever reported here. So I'll go for reporting the slew. And I am just clicking the values and pasting it here. So slews also can be picked up like this. And I'm adding mean rise, mean fall, max rise, max fall. So you can see that I have also analyzed the slew for this particular pin, and these values are different from each other. For the max analysis, these values are very close in the sense of they are in proximity of each other numerically, and these two are also numerically in the proximity of each other. However, the max analysis data and the mean analysis data are far apart. This is the way that you can analyze a pin by pin data of a design. Now again emphasizing, I have kept the pin constant because I am varying the commands here. You cannot vary everything at the same time. You have to keep one thing fixed and vary another thing for your analysis. For this is for demonstration, I have kept the pin fixed and I have varied the analysis type. So report slacks, report AT, report RAT, report slew. Case of actual design traversing, you will just keep the analysis fixed. That means whether you are analyzing the slew, you will keep the slew and vary the pin. That is how you traverse in the timing path. You get the pins I have already shown in the report timing command. So once you do the report timing, you get all the pins in a timing path. So timing path starts here. Here is the start point and here is the end point. So if you want to traverse from this to this, you get the first input, first pin here. The next corresponding pin is here. The next corresponding pin is here. Then you go downwards and this is the final pin. So if you want to analyze this pin wise, this path, you can use the same analysis. Say you are reporting slew, so you keep the reporting slew and whatever particular branch you are analyzing. So if you are using a max analysis, then you do the max, keep it constant and vary the pin and note down the data. This way you can traverse along a path, timing path, and get all the data, and then you can think upon the data where you have to modify to root out the violation. So this was the analysis part of the static timing analysis. That is how you analyze. And now let me clear the screen. Now I will show you some commands which will dump different analysis data as a whole. You will see how this works. These are dump commands. Dump underscore and then hit tab, so all these options come. Another thing, if you want to just have a kind of command line manual, you can type help. So this will invoke the help. So you can see here all our dump commands are here and they have a single switch only, except this particular one. They have a single switch and all the dump commands gives output as a file. So you can see -o file. Whereas when we use this particular commands, report slew, AT, slack, they have a pin and then they have a division like mean or max and subdivision like rise and fall. So this is the difference between the overall dumping and the pin-wise dumping. We vanish this particular So I am typing dump net load, then dash o net load dot. You can give any extension. I am giving report extension. So the data, whatever with us in the live shell, that data has been dumped into this particular file. We'll see how we can read them. For that, I have to open a terminal. I am clicking here, another terminal. So here, so let me see. How many report file have been created. So netload.rpt I can see. Let me invoke that with begin. So you can see here the file is created. So these are the branches. So this is the mean plus rise, mean plus fall, max plus rise, and max plus fall. And here you can see the net name. So here it is. This file you can get with a dump. So you can see all the nets are dumped and the corresponding loads have been dumped here. I'm closing the file right now and I'm going back to the Opentimer shell. So this was our normal Unix shell where we are operating, and here Opentimer shell is still alive. In the same way, we will dump slack we have dumped all slacks in the slack.report file. So dump 80, we have dumped the 80.report file. So we have dumped the R80. Another important dump command is dump ping f. I have used the dump command to dump all kind of the RPT files. So here, let me go back to the Unix terminal and do the ls report. Now you can see that we are in the same folder. 5 report files are there, which we have created using these 5 dump commands. Okay, these 5 dump commands, we have dumped 5 report file and they are created in the hard disk, the working area. So the first one which we dumped is a net load. So net load I have already shown you. The second one is the slack.rpt. Opening the slack.report file, mean plus rise, this is mean plus fall, this is max plus rise, and this is max plus fall. And here you get the pins. So this column is based on the what you are reporting, this column. So you have seen this particular file, so we'll do some comparison later on this session. So this is for 80, that is arrival time. We have mean plus rise, mean plus fall, max plus rise, and max plus fall. And here you can see all the pins. So when you keep one particular analysis constant and you traverse along the pins, right? So you can also get the data from here, overall reporting. It's up to you how you proceed. How you like to traverse, you can dump the report and then by hands-on calculation, you can traverse inside the timing path. The way is open to you. You can pick any method. So I am opening the R80. You can see the RAT file has opened, rat.report, 1, 2, 3, 4, 4 columns. Again, these are same columns already I have mentioned. And here the list of pins. We are, I think, major done. Did we missed anything? Net load already in the shown in the, okay, pin cap. Okay, let me on the pin cap. Pin cap dot report. Again, here pins are there and their capacitance values are there. You can see here the pin capacitance have been dumped. Close it. Mostly done with the part where we have dumped the data in two fashion. First fashion is that we are dumping the data pin wise when we are traversing pin by pin, and also we have reported the things as a overall to the entire design. So two ways you have already seen that how you can dump these things and play with these things. One option is going pin wise, another one is entire design wise. So both option has been shown to you. And the next part, we compare these pin wise versus the table. This is called a sanctity check. So this is, as a VLSI engineer, your duty is to check the sanctity of any report. So guys, let us proceed towards the side-by-side comparison. Here all the report files. Let me pick one file, and for that file I'll pick one particular pin. Okay, so let me grab the F1:D pin on which we are operating. So which one to pick? Okay, let's pick the RAT. It has gripped the F1:D pin and the 4 column values, first, second, third, fourth, we have got from the output report file. So let us go back to the Opentimer shell and let us do the one by one, that is pin by pin reporting for the F1:D pin. So let me do the access the data pin by pin data first, the 4 values, and then I'll compare with the table values. So we are ready with the 4 values that we have traversed pin wise. Here we keep the pin F1:D fixed, and we have done the mean plus rise and mean plus fall and max plus rise and max plus fall analysis of required arrival time, RAT. So 4 values are here. You can see, let me now compare the values. So here you can see the first value is 21.833. So you can see this value is the first one. Now 26.5. Here it is 26.5. The decimal places is varying as per the printing inside the file or printing inside the shell. Next is 71.8. So this is approximately 71.8 if we round off these two. Okay. And this is 76.3. So this is also, if we round off the decimal places, this is coming as 76.3. So this way we get the 4 values of mean plus rise, mean plus fall, max plus rise and max plus fall in the table. So here I have grabbed one row from the table for the F1:D. So let me do it for another particular file now. Okay, so here I don't see the Slew file. Let me dump Slew. So the slew.rpt is generated. Now let me grep from the slew report file. So we have these 4 values for f1:d. So here report view so let me first get the values one by one. So here we have reported the slew for f1:d. Now let us compare with the 4 column values that we have in the slew report file. The first one is 0.0987. So you can see if we round off, these values come. 0.0365. Here is the value rounded off. I think the next decimal points are rounded off. This is 0.428. So this is 0.428. This is exact match. And this is 0.426. This is 0.426. So we have verified and checked the sanctity for 2 different type of reporting. That is, one is report RAT, that is required arrival time, and the slew for one particular pin. So this way we do the side-by-side comparison. I think rest of the files you can try at your end and verify these things. We'll close today here. We're done with this side-by-side comparison. Hey guys, welcome to the 13th episode of Static Timing Analysis. We are continuing hands-on practical using Opentimer STA. Today, we will dive into the timing path tracing through Opentimer STA, where we will focus on node-by-node comparison between arrival time versus required arrival time for both the setup and hold violation scenarios. Stay tuned till the end of this episode for enhancing your knowledge on hands-on static timing analysis. Hey guys, welcome back. We are in our computer screen and we will start our exercise now. Let me launch Opentimer. So Opentimer shell has opened and we are in the directory where the Opentimer test case is already there. So let me do the ls. So it's simple. The test case name. We are entering into the directory. And here all the files are there. So let me load the files. So one by one I am loading the files here right now. So loading of the files are done right now. What we'll do right now is we'll do the report timing command first, just to do the internal timing analysis. So report time has run. So the internal timing engine has read all the files and it's now ready to accept our commands. So first what I'll do in today's exercise, we will traverse the path for one type of analysis, either hold or setup, any one of them. Then we'll do the same thing with the another one. So let's begin. So this is the report timing and I am giving mean. The mean is for the hold analysis. I am path tracing here. We are doing for the path which starts at input 1 and it ends at f1:d. And the analysis type is mean, which is actually the hold violation. And first we will do AT and RAT using the specific commands, and then at the final we will compare with the value of the slack this is coming. So that real-time work, you can actually follow this method to find out where issue getting injected. So let's start. And before beginning, I would like to remind you one thing, that in the timing report analysis episode, I have explained the slack equations, and for hold analysis and the setup analysis, the equation is a bit different. In case you have not seen, please see that episode to understand the slack equation. That will help you to understand today's episode. Without any further delay, let's begin. Report 80, then I give the pin name. Here input 1, and then I give, we are doing the mean analysis, so mean should be there, and if you look here, this is fall, so this has to be the fall branch. So when I give, it gives 0, so it is 0, you can see here, and we will proceed here. We will compare the result at the last. As soon as we proceed node by node, so this is a node and the next one is a node, the next one is a node, the values get accumulated. That means values are added with each other. We do not have absolute value, it's a kind of values are getting added once we progress to the path and node by node. When I am giving this, what I am doing here, next after pin, what we have, P1 colon A. So this is I am giving here, and this is 0, and let me proceed. So here it is rise. The next one again is, we are proceeding rise, and then this has changed to fall. If you follow this table, this has changed to fall, so I am changing it to fall. We have reached to the end node, and this is also false. So that's okay. You can see that 0, 0, 2.79, 2.79, and it gets accumulated. So whatever the values are here, it goes and it added. We can see here this arrival time. 80 is the arrival time. R80 is the required arrival time. So I'm looking at here the accumulated arrival time, or that is the total arrival time is here. We have traversed the path. Now let me traverse the path for the R80. I begin with the same again, here input 1, and I am just copying from here. So it gives this value. Let me proceed one by one. Now this was rise, so change this to rise, because here when I am picking, I should be picking in the corresponding branch. This is rise, the rise transition. So we are proceeding, and you can see that value is getting increased one by one. And let me go for the next node. Here this is final node we have reached. So here this is the 26.5 is the accumulated or the total required arrival time. Okay, this one. So you can see this is same as this. We already, when we reach the same node here, you can see that this was the arrival time. You can use the slack equation to calculate this slack. So this is how the engine actually internally traverses, and you can manually do that this single commands, or in case actual timing engine, you can write it this in a pickle script and you can source it and then compare. So that will be a very handy thing. That is the very beauty of pickle in these EDA tools, where you automate all the manual steps. For this, now you can see that whatever Slack, we are getting whatever the total accumulated arrival time and the total accumulated required arrival time. We have already by individual command, and we are traversing by the node. We have already rechecked the sanctity of this particular timing report. Thus, we are done. So this hold analysis, the mean analysis is a hold analysis, and we are done whatever our exercise. Now I'll clear the screen. So we are taking the max analysis, and this is for the setup violation. And here let me go one by one. Here in this path, this starts from F1:CLK and it finishes at the out, and this is max type analysis, that is setup violation we are checking. And here we start with this particular pin from the flip-flop, and we proceed further. So this way I'll continue further down. So we have come to the accumulated arrival time. You can see here the accumulated arrival time is same. So here it is rounded off, that's all, nothing else. So we have traversed the path, or traced the path from start point to end point using the commands individually. We have done for the 80, that is arrival time. Now we will do it for the required arrival time. Start with the first pin. So folks, you can see that we have done the 80 and RAT. So the accumulated 80, that is this one, we can see that here is the value, this arrival time. And once we trace the path from beginning to end, we also get the RAT, that is required arrival time. You can see here it is. And according to the Slack equations, the Slack is calculated and this has been violated. So this was a path tracing for setup violation, and earlier we have done this for a hold violation. We are done for today, and I'll clear the screen. Bye for today. Hey guys, welcome to the 14th episode of Static Timing Analysis. We are continuing hands-on practical using the Opentimer STA. Today, we will dive into the gate sizing to Opentimer STA, where we will cover the fundamentals behind the gate sizing to cure the STA violation. Stay tuned till the end of this episode for enhancing your knowledge on hands-on static timing analysis. Hey guys, welcome back. Today we are talking about gate sizing. So first we will discuss what is gate sizing and why. It's all about fixing the STA violations, specifically tuning the delay. So just to fix the timing violation, one important factor is the gate delay. And this gate sizing is all about tuning the gate delay to the right amount. We know that CMOS equal to PMOS plus NMOS. Why I'm saying this right now? Because the transistor delay is simply the multiplied product of R and C. R is inversely proportional to the width of the transistor. C is proportional to the size of the transistor. To reduce delay, we can decrease R, that is, increase the transistor width. In general practice, transistor length is kept fixed while the width is varied. Sizing an CMOS inverter by a factor 2 means that you make both the NMOS and the PMOS in the inverter twice as wide. This will behave in the same way that two standard inverters are in parallel. A 2x inverter will have a 2x stronger output. This means it can charge or discharge the load at its output 2x faster. So this way, we use the gate sizing method to tackle the gate delays at various points in a timing path. So we are done with the theoretical explanation here, and let's move on to the next section. Hey guys, welcome back. Let us go to the Opentimer website. So here we go. And why I'm coming here, in today's episode, we will take another test case which is different from all the previous episodes. So, in today's episode, we will use this particular example. The test case name is Sizer and it's a NAND gate 45 nanometer open cell library test case. You already know that today's episode is based on the gate sizing. So we are picking up this particular test case and I am right clicking here and opening it in a new tab. So from here, I am copying the path. So here I am in the terminal and I am using gh-clone to copy the test case from the GitHub URL to locally to my PC desktop. So I am pasting the copied URL and I am hitting enter. So it started copying the test case to my local desktop PC and it's done. So you can see the entire test case has been copied from GitHub to my local disk. I'll come back here. Before that, let me go back to the Opentimer website again. So here, let me open the Opentimer wiki and there we have the command manual. Okay, and if we go to the command manual, we are looking for particular command. Yes, here it is, repower gate. So in today's episode, this command will be used and let me tell you why. First, let me describe this particular command. The repower gate command repowers a gate with another cell. The new cell must have the same topology with the old cell. So basically, this means that I am sizing the gate here and definitely with different dimensions, and obviously I'm not replacing a NAND gate with a NOR gate. This is you I think understand very well. Then the functionality would change. We are not changing the functionality here. That is not the scope. What is our scope is that we will vary the gate size and from that we will fine tune the delay. This is our purpose. So for that we will be using this particular command. It has two arguments. First, gate name, which is actually the instance name, and cell name. This is a cell name from the .lib library, that is timing library. This is very plain and simple. So I think we are done here, and let me go to the terminal. We are here in the terminal. Let me open another parallel terminal which I will use for browsing the files, and this original terminal I will be using for the OperTimer shell. Let me go to the inside the directory. Okay, and here I do the same. Now here you can see that several files are there. Timing library episode I have mentioned there. These libraries are characterized for various corners. So you can see this is from the fast corner, this is from slow corner, this is worst low corner, this is low temperature corner, and this is typical. For today's analysis, we'll pick this particular typical library. Let's take the tour of the test case. First start with the Verilog file. Here is the Verilog file, and I have opened it through the GVim. You can see here the module description is here, and all these ports are classified here as an input and output. You can see here, and next you have all the interconnecting wires, and at the final section we have the instances. So here you can see we are dealing with the NAND 2 X2 cell, and there are 16 instances starting from 0 to 5. So all these are interwired by all these nets. Now let me show you this particular cell and the two other size of the same cell in the .lib, that is timing library, which I'll be using in today's exercise. Let me open the typical .lib. I'm using GVim, and let me make it zoom. Okay, here it is the red. We have to turn off this highlighting. This is very annoying to the eye. We have turned off the syntax highlighting here. Now I will search for the particular gate name here. Let me copy it from here, and I'll go back in the timing library and search it. Here the search result, you can see that this cell NAND 2x2 has area 1.33. Remember it. Now let me go for x1. Here you can see the area is 0.79. Okay. Now let me go further for the x4. You can see here it is 2.39. So you can understand that we will be doing the resizing of the gates, and this timing library already has the record which gate has how much area, and it is now clear to your mind. That is, if we sort from low to high, the first comes x1, then x2, and then x4. So we are starting with x2, we will move to x1, and then we will move to x4. Let me close it. The purpose is done here of this file, and the Verilog is also we are done. So in the repower gate we will be using this instance name and this particular cell name. Let me close it. Now there are some other files. SPEF file, yeah, this is new in this particular test case, which was not there in the previous test case which we have so far used. For the entire syntax description and details of this SPEF file I have already discussed in the SPEF file episode, that is PX episode. You can watch that episode already in the playlist, and also I'll provide the same thing in the description. So here you can see here the header section, then we have the DNet sections, and inside the DNet sections we have cap, race, all everything. So all the parasitics are with us in this particular test case. So let me close it. Another important factor is the design constant file. I'm opening it. I'll not go in detail because I have already created an episode on design constraints file. Please go ahead and watch that episode. That's also in the playlist, and I'll also provide the link in the description. So here it is the design constraints of this particular test case. They have been defined as per the syntax. So let me close it. So I think roughly we have done the tour of this particular test case and all the necessary files. In the next section, we will be doing the hands-on practice. I have cleared the screen. So folks, let's start the Opentimer. Our OpenTimer shell is ready. Let me do ILS. So let me load one by one the various files. Okay, I have loaded the cell lib. Then the Verilog file. Then the ref. Then the SDC file. So I have loaded the files. Now let me clear the screen. Files are loaded and I am running report timing now. So our timing engine has run. All the files have been parsed and internal calculations are done, and our shell is ready to take our inputs. We are with the native gates, and first let me print report area. Okay. Then let me do the report post negative slack, and there is TNS here. Report TNS, and you also report the leakage power. So with the native gate that is already in the design, we are having the area as 7.98. WNS is 8.56 with a minus sign. TNS is minus 33.1 and leakage power is 209. Now so I am using the repower gate, then the instance name. So here are all our instances. So here I am picking up the instance name and I am picking up the cell name. Now we have x2 in our native design. First I will change it to x1. We'll keep on doing this thing for all the instances. So here you can see there are 6 instances 0 to 5, and we have replaced all the gates with NAND to x1, which were originally NAND to x2. Let me run the report timing again. So I'll do the same things. Report area, report WNS, report TNS, and report leakage power. So if you can compare, so earlier the area was 7.98. Now since we have downsized the gate, it has become 4.79. WNS has become minus 8.67, which was this 8.56. TNS was 33.1 and it is 33.7. Leakage power is 104, which was 209. You see there is a significant difference in the numbers. Basically, this gate sizing has impacted the delay and hence the slacks are different. I'm copying this command, and here instead of x1 I am moving to x4. Okay, so this one, and I'll keep on doing for rest of the things. Here I have done changes 6 instances from instance 0 to instance 5, which were there in the original .verilog file. All these 5 things, it was originally x2. I have downsized them to x1. I have upsized them to x4. Let me run the report timing again. You can see here the slack is also different here and here. In each case, this is different. And let me print the area. Area is now 14.4, which was earlier when we downsized 4.79, and the original ones was 7.98. So you can see the significant area increase. WNS, and let me first print and then I will compare. Let me compare. The leakage power here comes 417, which when we downsized it was 104, and in original this was 209. So you can see the significant difference of the gate sizing, and that has actually happened inside this particular simulator. Okay, so this way we are checking the overall reporting of the gate sizing, and we can see that the TNS, when we have done the upsizing, right, it has become 32.1. When we downsized it, it was 33.7, and originally it is 33.1. So you can see that originally it was 33.1. If we upsize it, it has become 32.1. So these things are already impacted, and you can see the leakage power. Native one, the leakage power was 209, downscaling it was 104, and upscaling it is become 417, that is double of the native one. So folks, I think we are done with the resizing, and that's all for today. Hey guys, welcome to the 15th episode of Static Timing Analysis. We are continuing hands-on practical using Opentimer STA. Today we will dive into the PVT variation in gate sizing through Opentimer STA. Stay tuned till the end of this episode for enhancing your knowledge on hands-on static timing analysis. Hey guys, welcome back. We are continuing our hands-on practical using the Opentimer STA. In today's episode, we will be exploring different PVT corners, and one thing I would like to mention here that we do not randomly vary the PVT corner for the static timing analysis. We have some de facto rules that for the worst case, we choose a specific corner. From company to company, this may vary. In general, the thumb rule is for hold analysis with worst case, we use the fast corner, and for setup violation with the worst case analysis, we use the slow corner. We will begin our exercise with the hold analysis. First, here you can see 3 terminal is there, first, second and third. So I will be using the sizer test case, in which we have one particular NAND gate which has 3 versions, that is X2, X1 and X4. X1 is lesser area than X2 and X4 is higher area than X2. We'll start with X2, we'll downgrade to X1 and we upgrade to X4. This is what we have done in the last episode. Today what I will do, I will parallelly open the terminal. In each one I will open the Opentimer, and there in each case, in one I will use X1, another one I will X2, third one I will use the X4. Now this thing has to be done very carefully, and I will be using the repower gate command I have used in last episode. Since we do the worst case hold analysis with the fast corner, as you can see here, we have several corners here: fast, slow, force flow, low temperature, typical. Last episode we have used the typical. Today for hold we will use the fast corner. Okay, then let me start the exercise. The first Opentimer I have turned on. We are in the same directory in all of the terminals. You can see here, this is same. This is same, and here this is same. And also in the fourth one here, there we'll be using the Unix terminal, and here also we are in the same directory. So here, let me also launch Opentimer. So folks, Opentimer has been launched in the 3 terminals. Let me clear the terminal. Now we have Opentimer shell here. Also Opentimer shell here. And also Opentimer shell here. So first I do the ls. I will get the physical files. This is same as in the Unix terminal. Now let me load the files. So these are our read commands. I will read one by one. First, cell lib. I'm loading the cell lib. Then the Verilog file. Then the SDC file. Then the spef file. Then the timer file. All our files are loaded, and what I will do, simply the report timing, just to run the timing engine. So the timing engine has run. It has just come out with one particular worst case reporting here. And let me source the same commands in other shell. So for terminal 2 we are done. Let's do the same thing in terminal 3. So folks, in the 3 terminals, the Opentimer engine has run, and in the 3 terminal, it is ready. Now you can see here, we are using the NAND to X2. So X2 instance we are using. What I will do is that, and let me clear the screen. The screen is clear now. So in the 3 terminals, the Opentimer is ready, the timing engine has run, and we are ready to go. So what I will do, in the first terminal, I will use the instance X1. Here the X2 will remain as is, and here I will do the X4. For that repower gate, I will have to end the gates. So here I am changing the gate to X1, which is have a lesser area. So here we have the X1 instantiated. We have repowered the gate, that is we have done the gate sizing from X2 to X1 in the first terminal. So we have the sequence X1, X2 and X4. So I'll do the same repower gate command here. However, this will be X4. So here 0 to 5, all the instances I have instantiated and repowered the gate. That means I have done the gate sizing from X2 to X4 in the third terminal. So let me clear the screen. Then the screen is clear, and here also let me. So I'll do the report timing. So the mean analysis is for the old violation. So I have done the mean analysis here. So I'll execute the same thing in all the 3 shells. So let me see whether we have the same path here in X7 to NX23. Here we have NX7 to NX23. As I vary it only in the screen, some data is varying. Apart from all these, gate instance is fixed and their rise fall direction is same. So you can see there is no change in this and this column. Okay, let me do the same thing here. Again here we have starting point NX7, then NX23. It is same as that. So if I vary here, I can see only X4 is varying here to X2 and then X1. Okay, this column and this column remain same, except that means the pin is same except the gate instance which is varied. So folks, now first of all, when we do it sequentially, for us it is difficult to take a diff in between the 2 things, and here we are taking the diff in between the 3 different cases. So that's why I have made the parallel terminals in which we can look into the detail minutely and compare what is happening where. As you know that the first corner is chosen for the worst case hold analysis, and one thing I would like to mention here, the fixing of these violations, either the setup or the hold, there are several methods to do that, and this tool which we are using have very much limited capability. Obviously not only this tool, the industry standard STA tools, they also have limited capability. They can operate on the live shell or based on the whatever files we have fed, but beyond those files we can do some custom changes, maybe in the ECO, maybe in the Verilog description, maybe we are inserting some gate, adding some buffer, we are rerouting some path. All these options can come. So the STA tool is for analysis. Fixing of the violation has to be done as per the root cause analysis, and that has to be done by the designer judiciously, taking the decision whether it has to be done in the ECO step, or somewhere we have to do a rerouting, or somewhere we have to add some buffer or anything else. Gate sizing is a method that we can do easily inside the timing engine, and obviously that gate sizing, when we are getting all these gates, in this case we have very much limited amount of size. When we have the actual standard cell library, there we have a lot of variation, or even if you want, you can ask your vendor to provide various size of standard cells based on their height, that is track, like it may be 40, 60, 70, 90, 12T. These are track heights. So one single cell can have different track heights, and as we go up in the track height, the cell size increases. This is how you can use in an actual case. When you are learning, take this as a learning purpose, and later on you can, when you are actually inside the industry, you will get a lot of flexibility to fix the violations. Now let us come back to our own exercise that we are doing. Here first one we have X1 and the second one is x2. You can see the change here. First let us look in the change, and x4 is here. So our first goal of the exercise is done. We have done the gate sizing to the repower gate command, and now in each case we are doing the hold analysis by using the mean flag, and the worst case is dumped here. And in the three cases we can see the difference. Now if we have the x1, our slack is 8.605. I am ignoring the minus sign while I am talking, but you can see it in the screen. As we go to the x2, it becomes 8.492, and as we go here it becomes 8.282. So gradually, if you see that we move from x1 to x2 to x4, as we go higher in the size of the gate, what happens that this particular slack is the numerical value or the modulus value is reducing. That means we are proceeding towards the correction. Now this is not only the single correction. I already mentioned that there could be a different amount or different methods of fixing the STA violation. We are operating on the shell now, so whatever available in our shell I am showing you. But it is significantly, you can see that the slack has changed. Even you can see the change in this and this column, this delay and the time column. I have already explained first hands-on episode what are these columns and how to interpret them, or in the timing report. So there you can also go and see that particular episode. I'll provide the link in the description, or you can go to the playlist and find that particular video. Now here, this particular column and this particular column, you can see that in these two you will see the change. Not only here, you can see the changes here. The constant columns are this and this, except the instance, the pinner constant. So let me vary, and you can see the change in front of your eye. So it has changed. You can see that these and these columns is already changed. And again, when I go from here, you can see that it has also again changed. So the gate sizing is impacting on the final slack of this particular path. As we go higher in the size, it is reducing. Even there is a violation, the violation margin is reducing. So if we take some more measures, or if we had some bigger gate area, then this would have been reduced drastically, and this could be one of the method or one of the tools that we can use to fix the violation. So folks, here we are done with the particular analysis, and when you do something, it is whiz weak. That is, what you see is what you get, and here what you see is what you are actually getting. 8.605, then it goes down to 8.492, and then 8.282. So in this case, for the same path, we have varied the gate size, and we have seen a huge reduction in the slack. So here it is. And then we have to do a path analysis and see if we insert a buffer somewhere or do some changes in the routing, then whether this can be fixed completely. That is a different scope of the fixing. We will stay limited in the Opentimer shell, and here I am showing what things we can do here. We are done with the hold exercise. Let's move on to the setup analysis. Hey guys, welcome back. We will do the setup analysis now. Here you can see for the hold analysis, we have picked up the first case for the worst case analysis. And now we will pick the slow corner for the setup worst case analysis. I have the same configuration of the terminals here. First terminal will be for x1, second will be for x2, and third one will be for x4. And the fourth terminal I will use for playing around inside the Unix shell. Here, let me start the Opentimer in each of the cell. Remember that in this particular section, while doing the setup analysis, we will use the slow corner, and we will load this particular .lib file. So here, let me start the Opentimer in the three different shells. So first, second and third, the Opentimer is ready for all the cases. Let me clear the screen everywhere. So here 3 terminals are very much clear, and the 4th terminal is our Unix terminal. So I would like to start here. Let's start here. I'm doing a ls for the files, and there comes all of our read commands. So let me read there. .lib. Verilog is done. Next comes the SDC file. So SDC file is done. Then the spef is done. Finally, the timing is also done. I have done the report timing, and our shell is ready now. So let me do the same for all the 3 Opentimer shell. First, in every case, Opentimer terminal is ready, and let me clear the screens. And here let me grab the cells. These are our cells which are used in the design. By default, now all the cells have the instance NAND x2. 2 will remain same. Here I will use the repower gate. So here I'll downgrade it to x1. I'll do for all the instances. The middle one will stay with the original gate, that is x2, and the third one I'll change it to x4. So folks, we are done with the gate sizing using the repower gate command, and let me run again the report timing. So I have done the report timing here. Here also done. So let me clear the screen. Here the screen is clear. So in the 3 cases, the terminals are now ready with the setup analysis, and we are ready with the slow corner, the .lib file. Now in this particular case, we do not have any kind of setup violation. So what I'll do, So I'll do the max. So you can see this has come. Although this is not a violation, this is a path where the setup is met. Okay. And I'll do the same thing here. I'll do the same thing here. So you can see that this particular has changed in between this and this and this and this. So what I'll do, I'll pick one particular case, and in that case I'll pick the particular last node, and I will apply the report AT and RAT command, which is usually used for the calculation of the slack. I am picking one particular node, that is the endpoint, this and this. I am picking up this particular node for the report AT RAT command. So let me clear the screen. So the node is NX22. I have opened this once again just to fill up the particular command. Pin is NX22, and here when we come, we use the rise one. We are picking the rise case. We are using the max analysis. So you can see we have picked the max analysis, we are taking the rise, and we are picking the NX22 node. Here I'll do the same. I've done the leveling here. First case, the gate is X1, this is gate X2, and this is gate X4. So X1 has the smallest area, X2 has higher area than X1, and X4 has higher area than X2. And we are using the slow corner, the .liberty file, and for the setup analysis as we go for the max. Now what we have the AT, which we can see the RAT is same everywhere, because RAT is something that we set as a goal that has to be achieved, and what we achieve is contained in AT, and the difference of these two becomes the slack, and that is already discussed in the timing report episode where I have explained the slack equation. So here what we can see, that first case, for the smallest gate area, we have the AT is 2.77, and we have 2.99 for the X2, which has a much higher area, and for X4 we have AT 3.39, which is the highest of the three. So we can see for the setup analysis, for the lowest area we have the less arrival time. So in this case we have the AT 2.77, Here we have 82.99 and we have 3.39. I think it is now clear that what will happen in both the cases, that is both the worst cases for either the setup analysis or the hold analysis, and picking up the corresponding worst case library. We have seen in today's episode, in the two worst case scenario, if we do the gate sizing, what will be the impact on the slack, that is AT/RAT. So we are done here with the setup, and also we have come to the end of this episode. Hey guys, welcome to the 16th episode of Static Timing Analysis. We are continuing hands-on practical using Opentimer STA. Today, we will dive into the what-if-then analysis combined with gate sizing through Opentimer STA. Stay tuned till the end of this episode for enhancing your knowledge on hands-on static timing analysis. Hey guys, welcome back. Here in our computer screen, for today's episode, we will download one particular test case from Opentimer website. So let's go there. So this is our Opentimer website, the first result which has come. Let us go there. And let me scroll down to the examples. So in today's episode, we will be experimenting with this particular test case, timing driven optimization example plus incremental timing update. We will be downloading the optimizer test case. So here the path is ready. Let me copy it. Here we are ready with the terminal and we are in the Opentimer test case directory. So let me type chclone. Here I pasted. Let the test case clone. Meanwhile, let me tell you why I have kept 3 terminals. In the first terminal, I will do up to a certain point and stop there. In terminal 2, I will proceed with some further step till the end. And as usual, the third terminal will be our Unix terminal where we will do our Unix stuffs. Our test case is copied. Let us go into the directory. So I will be doing the same in the next terminal. Three different terminals. We are in the same folder, that is Opentimer test case /optimizer. So let me do a ls. So you can see there are several files are there. You are already familiar with this file extension and how we load these things. So for today's episode, I have made one shortcut, easy to use flowchart in text so that I can move faster instead of typing. So let me display it. This is steps.txt I have created. I'll come to it later. First, let me launch the Opentimer shell. In the first one and in the second one. The Opentimer shell has been launched in the first 2 terminals as I mentioned. Now, let me clear the screens. The screens are clear now. Now here there are 2 libraries are there in the test case and we are analyzing using both of them, and let's have a diff between them. So for that we are using the tkdiff command. Also you can take a gvimdiff command. Let the tkdiff open them. And as you can see that early is used for hold analysis and the late timing link is used for setup analysis. So here is our tk-diff. It has opened. You can see here library early and library late, and if I scroll down you can see the tk-diff has been highlighting the difference points. So early is here for the hold and late is for the setup. You can see the changes are there in the lookup table. You can see in the left and the right. So here you can see how these 1, 2, 3, these things are different. Obviously subsequent things are also different. Here you can scroll down and see the differences, and tk-diff is highlighting everything in detail. This way is only the LUT segments. The different LUT segments are different in between these two libs. So let me close it. You can browse and explore by your own. In case you don't have the tk-diff command, I'll provide the tk-diff installation command for Ubuntu in the description. So let me close it. So here let me quickly load the files. Today I'll take the shortcut here using my steps.txt. So here for the first terminal, we have made the terminal ready to continue our experiment. You can see here it is written added min cell lib as early and added max cell lib as late. So it has picked up two different libraries, mint for the setup and the hold part, and the command that we have used, that read cell lib early, we give the early.lib and we give the late flag and then we give the late.lib. So let me do the same thing here in the second terminal. So folks, again the second terminal is ready also, and let me just clear the screen. Before clearing the screen, I would like to pin this particular output pin, that is the endpoint D17. You can remember this one because later we will be experimenting on this particular pin. Let me clear. Since both are same, let me do this max analysis in one shell, means analysis in the another shell. I was just speaking about this G17, right? G17 is coming here. Again, we have G17. Similarly, for this case, for the mean analysis here, also going through here, this endpoint is different. So here we just flashed two different commands for mean and max analysis, and there are violations in both of them. That means we have the setup and hold both kind of violations in this particular test case. So let me clear the screen. So we are done up to this point. Now comes the part where I will do up to some point and then I will stop there, as I mentioned for terminal 1. So here what I will do, TNS, WNS, this one, report slack has been done, report 80, report R80, so we already done this report timing, so I am not going in this particular command. So I'll come to this command, not right now, later I will come. Here I will pause for this terminal 1 and I'll move on to terminal 2, where what I will do is I'll execute the next steps. So here what we can see in the Verilog file, if we open up, there is an instance 10, and for this case using the repower gate, which I have already explained in past episode. Here we will do the gate sizing here for this particular instance from the Verilog file, and let me do it. We have done. So terminal 1 remains unchanged, and in terminal 2 we are doing the changes. We will do some what if then steps. So these things I have explained to you when I was describing the Opentimer manual, where I also explained the timing reports theoretically to the slide. In the same episode I have this what if then cases. I'll also provide the link in the description of that particular episode so that you can go and see in detail. So here we'll insert a buffer into the design, and its syntax is insert get. Then the next field, this is the command insert get. The next one is that get instance name, the instance name where we are inserting, and the library cell name. Library cell name means the name which is there in the, at least in the .lib file, here whatever files are there. This goes our first what if then command. So then we will insert a net to connect. It's a simple command. Execute it, and we are done the entering the buffer, and then what we have done that we have insert the get, and then we have insert the net. And from Verilog we can again see that there is a instance 3 for node get. So what we will do with that, we will disconnect the pin Zn, you can see this Zn, and rewire it with the new net that we have defined. So tau net 1 which we have defined. So we will rewire this particular net with this particular pin. So the syntax is, first thing we will disconnect and then we will connect using these two commands, and the syntax is disconnect pin, then the pin name, and connect pin, then pin name. So we first disconnect this particular pin and then we connect the pin. Fine. So these steps are done. Now let's connect the newly inserted buffer in between the towgate 1 and net underscore 14. So townet 1 you are already inserted the net, and towgate 1 and net underscore 14. So you can see net 14 here, net 14 is here, and towgate 1 here we have already used towgate 1. So let's connect the re-inserted buffer in between towgate 1 and net 14. For that we are using the connect pin command here. And the second connect pin command. So you can see that A and Z are the two ports of the buffer. You can easily identify here and here. These two are the two ports of the buffer. Now in the test case it is already there ready, the SPEF file. As we have done the changes in the net, right, definitely the parasitics will change and the corresponding SPEF is also supplied in the test case. So we will take the difference of the before and the after SPEF using the tkdiff command. So let me do the tkdiff. You can see that in the DNet connection here net 14 is there, it's changed, towgate 1 has come here. So this way you can see multiple changes have been introduced in the original, the optimizer SPEF and the change SPEF. Here the name is change underscore 1.spef. So these two you can see here the difference, and if you keep on scrolling down you may see some more changes. If it is there, yeah, here it is. Here you can see the changes. And here is 2. So the change is very much evident. I'm not going in details. I've done a complete episode on SPEF. I'll provide the link in the description in case you want to see and explore by yourself. Obviously, you can go ahead and do that. I'll close this tkdiff window. And here. So we have done this up to this point, connecting this one. You can see. Now let us add this particular SPEF. We have done the change in the SPEF. Here what I will do, I'll do a report timing. You can see whatever changes we have done, it has incorporated the changes, it has loaded the SPEF and added the nets. Let me clear the screen. The first terminal was paused at this point. The second terminal we have moved up to a certain changes. Now let me print out these things in terminal 2. You can see now the result has come. So here, so you cannot see any particular changes using this particular command. We'll move on to the next step. We'll use the dump slack command in both of them. Okay, here and here. What I'll do, copy the output up to this point and paste the entire thing here in the Slack d4.txt. Come to terminal 2 here. I copy the entire thing. And I paste in the another file that is named slack after.txt. I save the file. Now let me take a tk-diff in between the two. So folks, when we finally use the dump slack command, we can see the significant difference. You can see the before.txt is in the left side and the after.txt in the right side. So this is from the left side pane and this is from the right side pane. You can see there has been a lot of change here in these columns: early rise, early fall, late rise, late fall, early rise, early fall, late rise, late fall. So all these columns you already know. You can see there is a significant change in the overall Slack report, which has got impacted because we have done, these are end slacks. So whatever you can see, these are end slack for all these pins. And since we have inserted a buffer and we have repowered a gate, it has impacted whatever nodes were around it. So this way, all these 4 branches of slacks are affected. You can see it has impacted this timing, what if then analysis and the repowered gate analysis we have packed together in this particular example. Folks, we have come to the end of this episode. I'll close it. Thank you for watching up to this point. Don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section below. And bye for today.